Good afternoon, everyone. I'm Yanlin from CMU. Today, I'm going to present MiniBox, a two-way sandbox for x86 native code. This is a joint work with Johnson McCune, Jim Newsome, Brent Baker, and Will Drewry from Google Inc., and my advisor, Adrian Perrig from CMU. So first, platform as a service is one of the most commercialized forms of cloud computing. There were already 1 million active applications running on the Google App Engine in 2012. And it's critical to protect the operating system from the large number of applications in the platform as a service cloud computing. Thus, in general, a sandbox is deployed on the system to protect the guest operating system. However, the current sandbox apparently provides only one-way protection that protects the operating system from malicious applications. And if there are malware or malicious code on the operating system, the application is exposed to the malicious code in the guest OS, which is not desired by customers. Then our goal in this work is to establish two-way sandbox. The two-way sandbox will provide two-way protections for x86 native code. The two-way protection includes OS protection and application protection. The OS protection protects a benign OS from a misbehaving application. And the application protection protects an application from a malicious operating systems. You may say, wait, Yanlin, this problem has been solved. This is not new. Why? For example, the Intel software guard extensions, the SGX, can provide very efficient hardware-based two-way memory isolation. TrustWizard, which was published by our team 4 years ago, can provide hypervisor or extended page table-based two-way memory isolations. All those systems can provide memory isolation very efficiently, while you still propose a two-way protection here. Okay, let's look into those systems very carefully. We will find that both Intel SGX or TrustWizard only isolate a piece of application logic, which we call as a PAL, which may be the security-sensitive part of the application from the OS. However, for the non-sensitive part of the application, it is not isolated from the OS. And for that part, it's possible that there are malware or malicious codes there, and the malware can compromise the OS if there are vulnerabilities in the operating system. We found that it's promising to combine a one-way sandbox with the isolation mechanism to provide two-way protections. This figure shows one combination option. Here we deploy one sandbox to confine the non-isolated part of application. However, the issue here is that the sandbox may expose a very large interface to the application. And also, the developers in this design need to split application into security-sensitive part application and the non-sensitive part of application, which require very large porting effort. Then we found another option, another combination option. In this combination, we deployed the sandbox into the isolated memory space, and we also deployed the application, the entire application in the isolated memory space. In this way, we can avoid the porting effort in previous design. However, in this design, the sandbox still exposes a very large interface to the application. And also, the recent research work demonstrates that it's possible that a malicious OS can compromise a protected process, a protected application, by retaining a carefully chosen sequence of system call return values to the sensitive system call, which is called IAGO tags. Thus, to establish a two-way sandbox, we also need to prevent or protect the application against the IAGO attacks. In summary, though it is promising to combine a one-way sandbox and a two-way memory isolation mechanism to establish a two-way protection, it's still very challenging. The challenges include, first, the system design of how to combine a one-way sandbox and a memory isolation mechanism to establish the two-way protection. Second, we need to minimize and secure the communication interface between the software modules for OS protection and the application. Finally, we also need to protect the application against the IAGO attacks. We don't have answer for those challenges right now, right? So in this work, we have the following contributions. First, we design, implement, and evaluate MiniBox, the first effort attempt to toward a practical two-way sandbox for x86 native applications. Second, we demonstrate it is possible to provide a minimized and a secure communication interface between software modules for OS protection and the application to protect against each other. Finally, we demonstrate it is possible to protect against the IAGO attacks and provide an efficient execution environment for the application. This is the outline of my talk today. First, I'm going to describe the assumptions and the attacker mode. Then I will describe the MiniBox design, implementation, and evaluations in details. Finally, I will describe the related work and then conclude our work. So let's see the assumptions. In our work for both application protection and OS protection, we are assuming that there are no physical attacks. For example, the attacker cannot compromise the CPU or the TPM chip on the system. Also, we assume that the attacker cannot break the cryptography primitives. For application protection, we are assuming that applications don't have memory safety bugs, for example, the buffer overflow bugs or insecure design. Protecting applications from buffer overflow vulnerabilities is beyond the scope of research work. For OS protection, we are assuming that the small system call interface that the operating system exposed to an application on MiniBox is free of vulnerabilities. And also, the OS doesn't have the concurrency vulnerabilities in the system call wrappers. So for application protection, we are assuming that OS is controlled by the attackers. The attacker may attempt to access the application's memory or attempt to perform IAGO attacks to compromise the application. For OS protection, we are assuming that the application is malicious and contains privileged instructions. For example, the privileged instruction may be able to break the software fault isolation mechanisms. In our work, the attacker may attempt to support or control the operating system. However, in our work, we don't prevent denial of service attack or set channel attacks. Here's an overview of MiniBox. MiniBox combines a one-way sandbox for x86 native code and a hypervisor-based two-way memory isolation mechanism to establish two-way protections. And instead of including all the one-way sandbox in the isolated memory space, we split the sandbox components into service runtime modules and OS protection modules. The service runtime modules is the software components in the one-way sandbox to support the application execution. And the OS protection modules is the software modules to conduct the OS protections, for example, the access control modules. And we include the service runtime in the isolated memory space established by the hypervisor with the application to support the application execution in the isolated environment. And MiniBox exposes a subset of the operating system call interface to the application. To prevent against IAGO attacks, we split the system calls exposed to the application into sensitive calls and non-sensitive calls. Then handle all the sensitive calls inside the isolated environment through a libOS. Finally, MiniBox minimize and secure the communication interface between OS protection modules and the application. Here's the architecture of the MiniBox system. First, we can see that a hypervisor is running under the system, and the hypervisor establishes efficient two-way memory isolation between the regular execution environment, including the OS and OS protection modules, and the mutually isolated execution environment we call as MIEE. In the MIEE, you can see that there's a x86 native application and the service runtime. The service runtime in our system design includes a context switch, which handles the context switch or the thread context switch between the application and the service runtime. I would like to mention that the context switch is the only interface that the application can switch into the service runtime. All the system calls must go through this context switch module. And in the service runtime, there's also a system call parameter marshalling that will marshal the system calls, the system calls parameters from the application, and also a system call dispatcher and the libOS. The system call dispatcher is going to distinguish the system calls from the application into sensitive system calls and non-sensitive system calls. For the non-sensitive system calls, the system call dispatcher is going to trigger an environment switch from the MIEE to the regular environment. And then the hypervisor is going to copy the system call parameters from the ME to the regular environment. Then the OS protection modules, the OS protection software components is going to take the control to conduct the OS protection work. For example, the OS protection module can conduct the system call parameter sanitizing or access control here. And then finally, forward the system calls to the operating system. For sensitive system calls, the system call dispatcher in the service runtime is going to forward the system calls to the libOS. For example, for the dynamic memory management, thread local storage management, and multi-threading or secure file, the libOS is going to handle all the system calls. So finally, as we mentioned, MiniBox provides minimized and secure communication interface between the OS protection modules and the application. How MiniBox achieves that? And first, during the load time, the only interface exposed between two components is the program loader that will just read the binary of the application, gets the code session or data session address, and then load the binary of the application into the isolated environment. So the program loader is very simple and exposes a very small interface. In runtime, the only communication interface between the two environments is the system call interface. And MiniBox secures a system call interface between the two environments in the following ways. First, the application specifies the system call information, including the system call number or parameters, the parameter type or parameter data. Then the hypervisor will pass the system call parameters and return values between the two environments. The OS protection module is going to check the system call information, including the system call number or parameters, and then only the legitimate parameters can be passed to the operating system. So MiniBox handles exceptions and interrupts in the hypervisor right now, and MiniBox can also support the debugging mode. In the debugging mode, the hypervisor-based isolation is disabled. Then the one application layer module is going to simulate the operations by the hypervisor and copy the system call parameters between the two environments. In this way, actually the application developer can use GDB to debug the applications that will run on MiniBox. So we implement a proof of concept prototype for MiniBox based on a public implementation of TrustVisor that we published 4 years ago, and Google Native Client open source project. Google Native Client is a one-way sandbox for x86 native code, and is already deployed in Chrome browser. Our current implementation can support multi-core and both Intel and AMD processors. The guest OS is Ubuntu. And in the original TrustVisor, there are about 14,000 lines of code. We add about 700 lines of code to the TrustVisor to support the two-way protection. And we are using the native client, Google Native Client ELF file loader to load the applications into the isolated environment. And we added about 300 lines of code to conduct the isolated environment registration or unregistration work. Finally, our implementation of the service runtime in the MIEE contain about 3,500 lines of code. So we evaluate MiniBox with macro benchmark and application benchmarks, including both IO-bound applications and CPU-bound applications. First, let's look at the macro benchmark for the system call overhead. We measure the system call overhead for applications running on MiniBox and compare the results with the corresponding system calls on MiniBox in debugging mode and the Google Native Client. First, let's look at the system calls that are handled by the operating system in the regular environment. Please note that for those system calls, and each system call will cause environment switch between the MIEE to the regular environment. And for those system calls, environment results shows that on MiniBox, those system calls had very high overhead compared with the result on MiniBox in debugging mode or NACL. However, in the debugging mode, those system calls have similar performance to the calls on NACL. Apparently, it shows that the hypervisor-based environment switch on MiniBox causes very high overhead for non-sensitive system calls. And then we look at the system calls that are handled inside the isolated environment, which are handled by the libOS. And we found that the system calls on NICO, on MiniBox, has similar performance to those system calls on NICO. So apparently it's a problem for us. And on MiniBox, the system calls that are handled by the regular environment has very high overhead. What? Then can we handle it? Then we measured a benchmark for IO-bound applications, which is a zlib application. The zlib application read 1 megabyte of file data from the file system in the regular system. So for each read of the application, there's the environment switch. And the zlib application comprises the data. And the measurement showed that zlib application has a very high overhead, very high overhead on MiniBox compared with NICO or MiniBox in debugging mode. How to solve it? Actually, to solve it, we add a cache buffer in the isolated environment to cache the data. And in the condition that all the data is cached in the isolated environment, which means that there's a cache hit, and the overhead is dramatically reduced, as shown in this figure. Thus, we can get the conclusion that though file I/O is very expensive on MiniBox, however, we expect that the cache buffer inside the isolated environment will improve the application performance in practice. We also evaluate MiniBox with CPU-bound applications, which is AES key search application and Bitcoin. We ported the open source implementation of Bitcoin onto to MiniBox. The AES key search encrypts 128 byte plain text for 200,000 times, and a Bitcoin performs 200,000 hash computations. The measurement results shows that MiniBox doesn't add any noticeable overhead to CPU-bound applications. Though there are many related work on protecting applications or Sandbox or OS protection, we found very few work on two-way Sandbox. The most related work is the ink tag that protects application against IAGO tags. In conclusion, we made the first attempt toward a practical two-way sandbox for x86 native code, and we proposed a generic architecture for establishing two-way protection. We anticipate that the MiniBox will be widely adopted on systems where two-way protection is desired. For example, a platform as a service cloud computing platforms. Thank you very much for your attention, and I will be very happy to take questions.
Maybe I'll ask one. I was wondering, what has been your experience in terms of how much work is it to port an application to run on top of MiniBox?
Yeah. This is a very good question. The question is how difficult to port application on MiniBox, or what's the porting effort? Actually, current implementation is using Google Native Client, and the Native Client paper already evaluated the porting effort, actually. They demonstrate that it takes only several hours to port internal implemented the video coder to NICO, and Native Client exposed a similar porting effort to NICO. However, the difference is that for porting applications to MiniBox, the developer must know how MiniBox handle two-way protections. For example, they must know that MiniBox is going to use the file I/O to protect the file contents, and then the developer must choose the file I/O API to protect the files. Also, actually, I didn't include details in the talk, and MiniBox can expose the virtual TPM APIs, and the application developer must know how to use the TPM APIs to protect the data. Thank you very much.